All right, so nice. So let's focus on digital electronics. So the first thing we need to learn, we need to know all the gates. Remember all the gates? Yeah. All right. So let us see. I think I have all of them here for you. I will send all this on the group. Hold on. Okay. Hold on, let me see if I have it in this. Oh no, that's the analog. There's some of them here, but this is not. All right. Let's say this could work, right? So here you have your logic gates, right? You have your not, your and, your or, your and, your no, your XOR, and your XNOR. Don't think you would have done XOR and XNOR before, right? But these are all your logic gates here. So if you look closely here, just a quick review, right? A quick review. The not, you will need to write this down because you'll need this for the whole class, right? The not gate, remember, single input. A 1 will give you a 0. A 0 will give you a 1. AND gate, 2 1s will give you a 1. But if you look here, watch this here. Instead of having to memorize this whole thing, here's what you can learn. For AND gate, once you have a 0, you're going to get a 0. Right? That's the rule for AND gate. A 0 will always give you a 0. Okay? So for AND gate, a 0 will always give you a 0. Okay? The OR gate, the summary different. A 1 will always give you a 1. A NAND gate, on the other hand, a 0 will give you a 1. A 1 will give you a 0 for a NOR. And the two new gates are the exclusive OR. So once you have a 1 and a 0, you'll always get a 1. And the exclusive NOR is the opposite. 2 1s will give you a 1, 2 zeros will give you a 1. All right. What I want you to do is to write this one down. I know you all like this screenshot, but write this one down because we're going to use all these gates now. The two most important gates are the one with the little blue stars there, the NAND gate and the NOR gate. Right? Those are the two most important gates. Copy down the gates and we're going to just look at how to use them. Right, I'll give you a small break in between, right? Pick a time, but I want you to highlight this. Highlight the summaries, right? Yeah, yeah. Thanks. Right, but X1, yeah, no, something, right? So these are all the gates. You have to learn the gates because in order to move on to the next part, you have to know these gates. But the summary is kind of easy. The zero given you one and so on. Finish. Oh, yeah. No, I said I did. No, I remember the job. I might get treated. They didn't know what to say. Common sense, we have to educate also. That's not what they. Yeah, All right. Yeah, right. So let's take a look at all these gates now. Next part of the gates, we need to be able to find equivalence. Before I do that, let's just do a quick example now. Let's connect them up. I wouldn't go too easy. Let's do a medium. So we have a NOT gate here, connecting up two NOT gates, and these NOT gates are connecting it up to a NOR gate. Right? So the first thing you do before you start to work it out, you label it up. There's a NOT gate, there's a NOT gate, and this is a NOR gate. This is A, these are your inputs, A. This is your first set of outputs, and what you recognize about those outputs, C and D. Those outputs, C and D, are the inputs for the NOR gate, right? Okay, so now we have A, B, C, D, E. Right? Let's see if we can work out. Let's see if we can work out this entire circuit here. Everybody remember what is called this table? A truth table, right? Yeah. So let's see if we can finish out this truth table. Those who are online, you all seen the last the 2 zeros? You all seen everything? Okay, I want to make sure. It cut off on my laptop computer. Right. Let's see if we can work it out now. C is what? C is the opposite of A, right? So that'll be what? 0, 0, 1, 1. What about D? D is the opposite of B. So that'll be 0, 1, 0, 1. And E is what? E is the output from a NOR gate, where C and D are the inputs. So let's see. So 0, 0 is, 0, 1 is, everything else is, right. quick question. These three gates, they behave as one. Anybody can tell me what that one gate is? These three gates are equivalent to a particular gate. Yes, so just figure it out. Ignore the middle. Correct, Shivani. Ignore the middle. Ignore C and D. Look at A, B. Look A, B, and E. As a AND gate. Yeah. Nice job. And you are correct. It's an AND gate. Are you okay with that? So learn the gates and you'll be able to convert. What you'll also recognize here is that the AND gate could be made by using three other gates, right? So what they did is instead of having to learn all those gates and having to always be able to develop all those gates, what they did is they say, here's what. Let's see if we could take a NOR gate and make every single gate. So we only have to make NOR gate circuits. And based on how you connect them, you'll be able to get an AND or a NOR or an AND or whatever, right? Right, there's a little circuitry I don't know. Let me check and see if I could use it here. There's a app that you could use. I think one is Simple Circuits. There's one called Digital Works. What's the one apps is used by? Huh? And next one, and there's using UV as well. But I use the free version, not the one that is using UV. I remember it as song. Right, and we'll get to put them together. So here's what we're gonna look at now. We're gonna generate all the gates using a NOR gate alone. Using NOR gates only. All right. So the first thing we want to be able to do is to create a NOT gate. Create a NOT gate using NORs. All right. This one's the one. This one kind of tricky. So remember a NOR gate. Yeah. Multi-sim. Right. I'm gonna see. You have it? No, oh, that was in the notes. Okay. Okay. It was multi-sim. Oh, wait, no. Or they have the app, or there's a. But you'll have it on the school app and this school computer. I don't have it. All right. So here's what you want to do. You want to get the NOR equivalence to everything. If you look here, this is the NOR equivalent of a NOT gate. Right? So what it is? How many inputs they have here? Right? They join them up. They join the inputs up and they kind of single the input, right? So what will happen here? You have input, output. So watch. One here will give you a 1 and a 1. 2 ones in a NOR gate giving you what? 2 ones in a NOR gate giving you a 0, right? If I were to change the inputs to 0, here will be 0 and 0. 0, 0 into a NOR gate is 1. And that's it. Technically, you created a NOR gate. Sorry, a NOT gate. You'll see that there is no way to get 1, 0 here because you have one input coming in. So you either have 2 1s or you have 2 0s. That's okay. So that is your NOT gate using NOR gates. Are you okay with that online? Rika, are you okay with that? Benicia, you okay with us? Right, so that's the first thing. So if I ask you to draw a NOT gate using a NOR, you have to draw this, right? Finish. Let's go on next. Let's go to our next one. Technically, you all could figure this one out. Oh wait, small note. Two nuts will cancel each other out. So if you connect two nuts, it don't make sense, right? Two nuts always cancel each other out, right? So watch what will happen here, right? If you have a one here, one will, the NOT gate will give you a zero, then the zero will give it back a one. So it doesn't really make sense that you have two NOT gates connected in parallel, connected in series, right? So make a note that two NOT gates cancel each other out. Two NOT gates cancel each other out. All right, nice. So whenever you're seeing that, you have to cancel it off here. You all remember this? I'll show you this. An AND gate could be made from two nuts and a NOR, right? But I show you this, right? And I just show you how to take a knot and make a, how to take a NOR and make a knot. So now we can turn this circuit, into all NORs. And look at here. See that? That's all NORs making an AND gate. So make a note of that. All NORs making an AND gate. Ready? Next one. Oh wait, I was supposed to show you this. How you will turn this into a NAND? How you could turn this AND gate into a NAND gate? How you could turn an AND into a NAND? Anybody? You can look back at your original circuits. How you could convert a AND into a NAND? Right? Correct. Celine. Any ideas, Eden? How to make a NAND from an AND? Huh? Use a OR. You getting there? Close to it. Close to it. Huh? No gates. Anything, any gate to put in front of AND to make it a NAND. Remember, NAND and AND are opposites. So how I can flip it around? Put a NOT, right? If I put a NOT in front here, that will convert to AND to a NAND. Correct? Are you okay with that? Look at the circuit. Look at the AND. AND is 1 0 0 0, right? And if I NOT it, you'll get 0 1 1 1, which is a NAND gate. Okay? So all I have to do is to NOT a NAND and not a AND to get a NAND. So if I wanted no gates alone, all I have to do is connect an X NOR gate here. Right? Now I have those 4 giving me a NAND. Okay? Right? Draw that here. All right, let's see what. And so watch here now. So we have just created a lot of gates, right? And as I told you, you don't want to have all these gates. You don't want to have to build circuits for all these gates. So what you have is something called a quad NOR chip. So you have this chip. It's called a quad NOR chip. And you have 4 nodes. And from this, you can build all the basic gates. Okay? So suppose you wanted a NOT. Suppose you wanted a NOT, all you have to do is single the input and connect the input through it. We're just using one alone. That'll give you a NOT. Correct? Suppose you wanted a AND. Well, make two NOTs and connect those NOTs up here. Now that same circuit giving you AND gate. That's okay? Andy? Suppose you wanted a NOR. Sorry, well, if you have a NOR, you just use this, right? Yeah? Suppose you wanted a NAND. Create a NOT here and connect it up like this. You have a NAND gate. Right? Suppose you wanted a hold on. Suppose you wanted a NOR gate. You already have it here. Suppose you wanted an OR gate, then connect the NOR to a NOT. Right? NOR connected to a NOT will cancel off the end, and you'll get OR. That's okay? So if they ask you to use a quad NOR chip to make anything, all you have to do is just make the right connections. And that's it. Okay? To make a NOR, right? To make a NAND. So just show this a minute. So you will know how to connect it up. So you'll see in your past papers, take this quad NOR chip and they ask you to create something. So that's what they mean by quad NOR. You don't have to use all chips, right? You're just using what you need. Right, so that's how to use the quad NOR chip. Right, this is fairly simple, it's just you have to learn all the games. Anybody writing online? Rahul, are you okay there? Let's put Pyong Master too. Physics, I mean physics. Next second. Yeah, okay, good. Right. Right. So I think I had, oh yeah. Wait, what was this one then, boy? XOR. Let's see if we can build a circuit for this one. Let's see if we can build a circuit for this one here. Sorry, a truth table. I gave you the circuit. See if we can build the truth table and tell me what you get in here. I think you're supposed to get XOR, right? Tell me if you get that. You're supposed to get XOR. So take this circuit and I want you to build this circuit for me. Sorry, not build this circuit. You know what I mean? Do the truth table. A, B, C, D, E. Right? See if we can build this truth table for me. Right, build it out. Just tell me if you get the XOR, right? Yes or no. Just message yes or no if you get it. And then the challenge now is to convert that to nodes of the nodes of the might figure it out. So you want to convert that to nodes only. But make sure it's working out, right? Work out CDNE and it should be an XOR. Yeah, you want to still get XOR. So you're taking off the AND and you can taking off the We know, or the leave knows the one, right? And then you gotta connect it up. Right, so that's message if you get the O, right? If you get the XO. Do the truth table, work out C, D, and E. Right, so you should get the gates already. You should complete the truth table already. So C will be 1, 0, 0, 0, because that's an AND. A and B giving you D. So that's a no, right? So that'll be 1, 0, 0, 0. And E is also a no. So this will be 0, 1, 1, 0. So yes, it's an XOR gate. Okay, nice. But here we need to have no's alone. So we had to get rid of this. Get rid of that and put in a no gate. Aiden, you know start. Be honest with me. I know I see your name yesterday, I wasn't sure. Right, in the holidays, I mean, when school we open, I'll send you the timetable. Wednesdays say the same. When you're at physics for? It's Fridays now. So it's Wednesday and Friday. Yes. 5 to half 6. I'll send you the timetable. So you'll have that. Because lessons is Monday, Wednesday, Friday. All right, let's check it out. So here, what I did, right? What I did is instead of using a AND gate, I took off the AND gate and I used this here. So now you have the OR equivalent, the no equivalent of the XOR. I know it's telling to remember. There is a picture or a little chart I will send you. I think the what's called some book again? Concise. The concise of a nice little chart with all of this in it. Real nice. I'll send you a picture, everything in case you don't have. Right, so if a question asks draw the no equivalent for XOR, you have to be able to draw this. Nice. Okay, good. So we have the XOR, right? I'll give it the, so you see how we learned all the NOR equivalents? We have to also learn the NAND equivalents, right? So for each one of these circuits, we could use NAND gates to work out all. Okay. And I'll show you how. You can probably start with the homework. All right, so here's what we're going to do. We're going to do the questions here. Let's start here. What gate is number 1? So instead of a gate, they have switches, right? Those who do not apply, you will see this in module 1. You have 2 switches in series here. Will that turn on the bulb? Will that turn on the bulb? Nope. Bulb is off. Right? Bulb is off there. So we can figure out the rest and what gate it represents. Oh, I'll give that quick guess now, right? I'll give that a little bit. You have to figure out what bulb make the bulb light, and then that's the gate represents. That's the gate represents a gate. And then and somebody said, what you all got online? So 0, 1 will be 0, 1, 0 will be 0, 1, 1 will be 1. So that is an AND gate. As an AND.
Yeah, and just thought
AND and a? All right, let's see. 0, 0, 0, 1, 1, 0, 1, 1. What you all got for this one online? What you get for this one? Come on, what do you think? Celine, correct. Karina, correct. Are you sure? Check it back one more time. Remember, 0 is like it open and 1 is like it closed. So think about it again. Think about what gate 2 represents. Yeah. Right, so you are correct. 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, 1, 1 is that. So it's an OR gate. Okay. So those who do applied maths and they ask you to do a switching circuit, these are switching circuits. Applied real nice and easy. Easier than P. I could probably say that. Yeah. No. Yeah. You can't count. You can't. You know, 2 are a little more challenging. 1 module hard. Just 1 module. But if you do in physics, it'll be easy. All right, nice. See if we can do these. Oh, that's how I went for the past papers. Hold on, coming back. Kind of. It's not textbook, it's the guy who used to write the past papers before 2019, somewhere around there. There's his booklet. There's a booklet he gave us while we were marking. So it's kind of like Right, let's check out B part 3 now. What you all got there? If you're not a no, you'll get a. If you're not a no, you'll get a. Or, correct. If you're not a NAND, you'll get a. And, correct. And you all did see? No, you didn't see? Okay, nice. So I'll see there. Right? You all recognize that this is a NOT gate, right? It's a NOT gate using NANDs. Single input. Anytime you see a single input, the only single input gate is a NOT. So that's a NOT, that's a NOT, and that's a NAND. Check it out and see. So just to make sure you're doing it right, X should be 1, 1, 0, 0. Work out Y, and then work out Q. And see what gate is up. Those who online can message, please. Y is what again? Y is 1, 0, 1, 0. And Q is what? Q is a NAND gate, right? So that'll be 0, 1, 1, 1. X and Y into a NAND gate, right? So what does this gate represent? What does this gateway represent here?
Oh, that's not. Oh, that's
What gate is that? Check it back again, Shivani. Are you sure? All again, none.
No.
Is that?
No.
Oh. Check it and see. 0, 0. By the way, take a look at the inputs and the outputs. Eh? Don't look at the outputs alone. Some of you are looking at the outputs alone. 0, 0 giving you 0. 0, 1 giving you 1. 1, 0 giving you 1. 1, 1 giving you 1. What is the OR gate? Very good, Shivani and Jude and Celine. Is that OR gate? Okay? It's an OR gate. Okay, next one. Right. What do you all think this means here? Suppose you never saw this before and they want you to figure out the output. Right? So you have an input there. You all see the dark lines? The dark lines are the input. And the input for A and B going into a NAND gate. What will the output be? What do you all think this represents? And then this. Huh? Yeah, correct. The bottom here is a 0, the valley is a 0, and the hill is a 1. So here what you have 0 here, 1 here, 1 here, 1 here, 0, 0, 1, 0, 0, 1, 1, 1. What do you all think? So we had to draw it, right? We have to draw it. So anybody can help me? So let's take a look at the first one here. 0, 1 into a NAND gate is what? 0, 1 into a NAND gate is? NAND. 1, right? Good. 1. So you see why it's important to learn that, right, Olia? I think I have a Kahoot on that. We have to give all that every class. So the answer is 1. Then you have 1, 1. 1, 1 in a NAND gate is what? 0. So you're coming down. Then you have 0, 0 in a NAND gate is 1. So you're coming back up. 1, 0 in a NAND gate is. So you're staying right here. 0, 1 in a NAND gate is 1. So you're staying right here. 1, 1 is coming back down. Right? So instead of giving you a truth table, they could give you the signals looking like this. Okay? Sorry, but you gotta draw it. And then work out XOR. Try and get boxes, right? And we'll work out the XOR for now. But just draw it neat enough. Make sure the inputs line up with the outputs. Right? Do the AND and the XOR. And then I think you can take a break. Or let it go anyway, or let's stay in. Yeah, done. No, no, you gotta send the answers. I just gonna show it. Right, let's do the XOR. So the XOR, you should get a 1 here, a 0 here, a 0 here, 1 here, 1 here, 0. All you get that? All right, nice. Okay, good. Take a little break. I think we did a chip already. All right, take a little break. Take a 10 minutes. 12. What time it is? Yeah, take 12. Quarter past, we start back and we continue with this module. Right online. Quarter past, we start back, right?
I just dream scan. Oh, are you done?
Ready? All right, let's go again. Oh, other one, and then coffee or okay. Oh, got time out of them. Now get it. All right, so next we're gonna take a look at binary addition. All right. Before we do binary addition, we have to learn how to convert. Well, you would have done this already in Form 1 or 2. Decimal to binary. What is? Okay, go ahead. Yeah, come sorry. Hold on, I find this guy so I can get disconnected here. All right, so you may or may not remember that the decimal system is to the base 10. The binary system, on the other hand, is to the base 2, right? So the binary system goes like this: 2 to the 0, the first set of values are the units; 2 to the 1, the second set of values represented twos; then 2 to the 2 is fours, and then 2 to the 3, and so on, right? I'm not going that far. So I am going up to, in fact, all right, I will go up to 3 bits, right? 4 bits. So 0 in binary is 0, 0, 0, 0, right? I'll do 4 bit, right? 1 in binary is what? 1 will be 0, 0, 0, 1. Okay? Because remember, the first column, right? This one here is ones. This one here is twos. This one here is fours. This one here is eights. Okay? How are we going to get 2 in binary? Right. 2 in binary will be a 0 here, 0 here, 0 here, and a 1 here. Right? Online? Are you okay with that? Rika, Karina, are you okay with that? Right? 3 is what? 3 is a 0 here, 0 here, 1 and a 1. Right? Because remember, this value here is 2, this value here is 1. So when you add it, you'll get 3. Okay? All right, let's see if we can finish it out now. I might be able to fit it here, but see if we could do 4, 5, 6, 7, and even 8. Let's see if we can reach up to 8. Right, see if we can reach up until 8. Right? Let's check it out. 4 is 0, 1, 0, 0. 5 is 0, 1, 0, 1. 6, 0, 1, 1, 0. Correct? 7 is 0, 1, 1, 1. And 8 is 1, 0, 0, 0. All right? So we're going to learn to add binary now. Whatever do that. You'll do this circuit for you too. The added chip on the full up. No?
Yeah.
I'll look for this simulation on it just now. Everybody okay with that? Trouble done? Trouble? So which one? You understand 4? No? Okay. So let's start back here. Remember, this entire column here is ones, right? So you multiply the value by 1. This entire column is 2's. So you multiply the 0 and the 1 by 2. Next is 4's, then is 8's, right? So let's take, for example, trying to figure out 4, right? 4, since this entire column here is 4, all I have to do is put a 1 here and 0 everywhere else. And that's 4. To get 5 now, I have to add on 1, right? You can lock down there. Okay, you can lock down there, right? 5 is 4 and add 1, right? So I'll leave in the 4 here and I'm going to add 1 down here. 6 is what? 4 and 2. So I add the 4s and 2s. And I put 0s everywhere else. Right? And the same way I figure out 7 and 8. You sure? So what do you think 9 will be? 8 is 1, 0, 0, 0. What would 9 be then? You already have 8. So I think 9 will be. And yes, you want to get one more, right? So where do you put the 1? In the 4's column, the 2's column, or the 1 column? In the 1's, yeah, correct. So 9 will be 1, 0, 0, 1. This is 8. This is 4, 2, 1. 8 by 1 plus 0 plus 0 plus 1 by 1, which is 1. Right? 8 plus 1 is 9. Okay? That's all. It's how to figure out where to put the 1. All right, nice. They wouldn't really ask you anything on that. What they would ask you on addition. So what we're going to do is do binary addition and then develop into the gates that will do that for you. Okay? So let's take a look at binary addition. Suppose I gave you 1, 1, 1, 1, 0, 1, and ask to add that up, right? Just as a quick review, what is 75 plus 89? In order for you to work it, you add your 5 and your 9. 5 and your 9 is 14, right? You have a value, which is called your sum. You put that 4 there, and then the 1 you carry in it here. That's okay? And then you add the 1 plus 7 is 8. 8 and 8 is 16. Are you okay with that? So you have a sum and a carry, right? When you add the values, and the value is bigger than 10 in this case, your carry part and your sum part. Okay, so let's add in binary now, right? We have a sum and a carry all the time. So there are some rules that we need to learn about binary, right? So we're going to have a sum and a carry all the time. And we have to learn the different displays. So like what is 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1, 1 plus 1 plus 1. All right, let's see if we can figure this out. Hello. Anyways. What's up? Sorry again, Olive. Sorry about that. Right, so you want to know how to get sum and carry, right? So 0 plus 0 is 0, right? So that'll be sum 0, carry 0, right? 0 and 1 is 1, right? So 0 and 1 is 1, so that'll be 0, 1 here. That making sense? 1 plus 0 is 1, right? And how do you represent 1? And 0, 1? Yeah? I'm about to show you that, right? What about 1, 0? 1 plus 0 is also 0, 1, right? So you're carrying across 0 and the sum is 1. But what about 1, 1? Right, 1 plus 1 is 2. If you look at your binary, 2 is what? 1, 0. Forget the zeros in front. That's okay? What about 1, 1, 1? 1, 1, 1 is 3, right? Right? 1, 1, 1 is 3. So 3 is 1, 1. So I put in 1 here, 1 here. Everybody okay with that? So now we're carrying this across to addition. Right? Now we carry this across to addition. Right. So let's start now. So binary addition. Starting right here. 1 plus 1 is coming here. 1 plus 1 is carry 1, sum 0. So the 0 coming here and the 1 going up here. That's okay? Now we're doing the next column. The next column here is 1, 1, 0. What is 1, 1, 0? 1, 1, 0 is 2, which is the same as, all right, I'll write it in red, sorry, blue, which is the same as 1, 0. So again, your 0 will come here and your 1 will carry all the way here. And we know that 1, 1, 1 in binary is 1, 1. Are we done? We're going to do plenty more. I'm going to make sure you understand it. Right, so I explain it one more time. 1 plus 1 is 1, 0. The 0 comes here and the 1 comes up here. 1 plus 1 plus 0 is 2. So I put 1 0 here. The 0 comes here because that's your sum, and the carry goes across to the next column. Now you have 1 plus 1 plus 1. Right? 1 plus 1 plus 1 is right here. Right? This part right here. 1 plus 1 plus 1 is 1 1. So I wrote it there. So your answer is 1 1 0 0. That's okay? How much is that? What's 1 1 0 0 in binary? Sorry, in decimal. 8 and 4, 12, correct. 8 and 12 is 4. Sorry, you know what I mean? 8 and 4 is 12, sorry. 8 and 4 is 12. And if you look closely here, this value is 7, I think, here, and this is 5, giving it 12. Right? So it's supposed to work out, right, Aidan? Online, are you okay with binary addition? Rahul, you okay? Yeah.
Does it stick with before? If it doesn't, so
No, we don't do more than 4. Because our purpose is not really addition, and our purpose is to do the circuit first. Right? We have plenty more to make sure you catch it, right? Anybody writing online? All right, let's go again. So let's make sure we understand this, right? What is 1 1 1 plus 0 1 1? I'll give you a minute to try it. If you can't, I will help you. All right, let's see what you got. All right, so we start in here. 1 plus 1, that's 1 0. 0 coming here, the 1 going up here. Right? Now you have 1 1 1. 1 1 1 is 1 1. So 1 coming here, and the next one going all the way up top here. 1 1 0 is like 2, right? So 2 is what? 1 0, right? So the 0 comes here, and the 1 comes here. So the answer is 1 0 1 0. Okay? You're okay with that? Let's go again. One more. One more, then I want to show you the circuit We have to figure out a circuit now that will give us all of this. Okay. Anybody confused? One more. 1, 1, 1 plus 1, 1, 1. 1, 1, 1 plus 1, 1, 1. Try to add that. Online message answers. All right, let's see what you got. 1, 1, 1, 1 is 1, 0, 0 here, 1 here. 1, 1, 1 is 1, 1, 1 here, 1 here. 1, 1, 1 is 1, 1. First one comes here, next one comes here. Does it? 3 ones and a 0. Now we need to learn how to create a chip that will do this first. All right. You'll recognize two things. The inputs here. You only have two inputs here. Realize that? That is done by what we call a half adder. Because he only doing half the addition basically. He can only handle two inputs. Adder. Half adder. If you look here now, you have three inputs. That is done by two half adders, which we call, well, a little more than two half adders, but we call that a full adder. And then there's a next one here. This is also a full adder. When you combine those three in one circuit, All three is called a adder chip. Is it two and a half? It's called a adder chip, right? It's called a adder chip. So make a note of that, and then we are going to investigate. We are going to look at half adders and full adders. Right, so watch back here. Anybody can tell me what gate is what gate? Look at this, right? What logic gate I could use to give mass carry? Focus on here, and then focus on here. What circuit I could use to give me carry? Correct, Jude. AND gate, correct. So AND gate could work here, right? Because 2 zeros giving you a 0, 2 ones giving you a 1, and so on. Next one is a XOR. So I could build a binary. I can build a half adder by using a AND gate and a XOR gate. That's okay. So let's see if we can build it. Right, let's see if this simulation here will work, right? Wait, now this thing don't give me any functions. Where is the gates? All right. Let's use the gates from here. So as I said, we could use an AND gate. Well, yeah, well, let me use a gate now. All right, normally you could just add on these things. I don't know what happened in here. You just drag it and put it there. All right, I don't know what I'm doing wrong. Let's change the simulation faster. It used to work. If I could do it on the computer instead. All right. Right, we take a little while, but we should be able to, if I could just toggle it right. So if you look here, we're trying to figure out sum and carry, right? We said the AND gate could do the what? Carry. And the OR gate in the XOR will give you the sum. Correct? So let's see what 1 1 0 given us. Right? Let's see what 1 0 given us. Just lost it. No, I'm not going to do that over. No, forget that. I ain't gonna draw it over. All right, so sorry. So let's focus on the half adder. I'll draw it then. I didn't save it then, I lost it. All right, so we have our inputs. Normally you just have sum on top. So we have the exclusive on top. And underneath we have the AND gate. This will give a carry. Okay, so let's just check and see. What was 1, 1 again? 1, 1 was what? Carry 1, sum 0, right? Remember that? So let's see if this circuit working. 1, 1. 1, 1 into a exclusive or is 0. So that looking good because your sum is 0. 1, 1 into AND gate is 1. So yes, circuit working. That's a carry. That's okay. So that is your half adder circuit. Well, that's one version of it. That's the one that we'll use for now. Or you could play around with it logically, right? Or any other online simulations that is good. Ready? The half adder, the small little note. The half adder performs the addition of the first column in a binary addition. The half adder performs the first column addition in the binary in a binary addition. Okay, that sounds too good, but the first column, right? So the first column, the half adder is used to add those two in the binary addition. In a binary addition. In a binary addition. First up, the half adder can only handle 2 inputs. The half adder can only handle 2 inputs. And the circuit is given above. And the circuit is given above. Full stop. Its box diagram looks as follows. So instead of drawing this circuit, you could just draw a box diagram. Right, so the box diagram, you just put in half adder. You're putting in two inputs here, I1, I2, and you put in sum here, carry. So you don't have to draw the circuit all the time. Right, for sum, that's good enough there.
We didn't go somewhere, we didn't multiply stuff like
F?
that. You have to draw a multiply to
For the organized with the teacher to come side lessons. Some September. Political game no, political game no, while if we sort of stuff.
He's not doing the teacher, he does something who has like three teachers, the other teacher at the farm side, she also she's in job.
Oh, she will give the unit 2 lessons in Miss Sanita. Okay. Okay, so that's the half adder. So that's part of it being done. Let's take a look at the full adder now. Full adder. Right. Do I give you this circuit? I'll give you the box diagram and make you do the circuit. So the full adder, write this down. The full adder can handle 3 inputs. The full adder can handle 3 inputs. And performs the addition of the remaining columns and performs the addition of the remaining columns of the binary addition. Full stop. It comprises of 2 half adders and the OR gate. So watch it here. I'm going to show you how to connect it up, right? Here's how it works. So you have your I1 and your I2, that's it, 2 inputs, and you have your I3. This I3 is your previous carry. So the sum will go here. And then the carry from this half adder would go here. This is half adder, this is a half adder. And then I3 and the sum will give you the final sum and the next carry that goes here. So let's call this sum 1, carry 1, carry 2. Those 2 into the OR gate will give you the final carry. All right, copy down. I want to show you how it will work. 1, let's do 1, 1, 0 and see how it will work. So it's 2 half adder connected like that and an OR gate. So it's made up of 2 half adders and an OR gate. That's the box diagram, right? The circuit diagram, we'll have to just connect up the half adders from before. Right, so I'll do a copy down, I'll do an example for you to show you how the full adder works. So the main difference between the half and the full is that the full can handle 3 inputs and the half can only handle 2 inputs. Okay, so watch here. 1, 1 and a half adder is carry 1, sum 0. 0, 0 and a half adder is sum 0, carry 0. 0, 1 into OR gate is 1. So your final answer is sum 0, carry 1. Check it back and see. That's exactly what we had. So 1, 1, 0 is 0, 1. Well, actually, let me keep it consistent, right? Let me put sum first and then carry first and then sum. Right, let me just do it over again while you're writing. 1, 1, 0, right? 1, 1 into a half adder is sum 0, carry 1. 0, 0 into on this half adder now. 0, 0 into a half adder is sum 0, carry 0. Now I have a 1 and a 0 going into OR gate. That'll give me 1. So my final carry is 1 and my final sum is 0. That's what I have here. All right. I want to give you one to do. See if you can figure out what the final sum and carry is. Online, you can message, right? What is 1? Sorry. What is I1 is 1, I2 is 1, and I3 is 1. 1, 1, 1 in a full adder. You should know the answer, so see if you're getting it. 1, 1, 1. Message your answer. Right? Message online. All right, nice. Good. So 111 is correct. So 1 start doing it out here. I'll write it in blue. 1 into a half adder is sum 0 carry 1. 1 0 into a half adder is sum 0 carry 1. Oh wait, no, wrong thing. The sum 1 carry 0. Sum 1 carry 0. 0 1 into OR gate is 1. So your final answer is 1 1. Okay, so that's the half adder. Last thing. Last thing is the adder chip. So we're going to do a box diagram for adder chip. Oh, before I forget for homework, if you guys do them things. Homework, I want you to take off this half adder and put the circuit diagram and connect it up. So I do want the box diagram. I want you to do the circuit diagram for the full adder. So all you have to do is go back to the half adder and take this off. Put the circuit in there. Also put the circuit in here. Okay, so do the circuit diagram for the full adder. And let's wrap up with the adder chip. Right. If we are to perform this addition, what do we need? We need number 1 here. We need a half adder. Here, a full adder. Here, a full adder. So we need a half and 2 fulls. Okay, so all we need to do is do a little block diagram. Are we done? I want to show you how to connect it up. Right? What you see? Your first 2 inputs go in here, your next 2 inputs here, your next 2 inputs here. Right? This will have a carry, this will have a sum. Right? This will have a sum, this will have a carry. Same thing here. And you're putting in all your values. 0 1 1 0 1 1. And you work it out. Right? That is your adder chip. I'm going to show you quickly how to work it out. 0 1 into a half adder is sum 1 carry 0. 0 1 0 in a full adder, sum 1 carry 0. 1 1 1 0 will be sum sum 0 carry 1. Right? So if you do the addition here, 0 1 is 1 1 0 1. So how do you read the answer? You start from here, your most significant bit. You read in here, you read in here, you read in here, and here. This will be your least significant bit. So the answer, you're reading upwards, is 1 0 1 1. And there's plenty, but I just want you to have a good idea of how to do the adder chip. Right? We could probably try it on a circuit. Next day, we could do one on a circuit. So the first column is a half adder, all the others are full adders. Draw the block diagram and connect it up. Please remember that this is your sum, and this one is the carry. All right, good. Consider that is your first part up until full adder chip, sorry.